Hello, everyone. Today I'm going to talk about distributed deep learning and GPU acceleration with Spark 3.0 with Cisco Data Intelligence Platform. My name is Mohammad Afzal. I'm engineering architect for big data and AI solutions in Cisco UCS Solutions Engineering Group. I'll be covering this topic with Ryan Lee, who is a systems software engineer at NVIDIA. Within organizations, datasets are growing with tremendous velocity, and petabytes of data is becoming norm. At the same time, in order to gain competitive edge, AI core technologies are also gaining tremendous focus to utilize this data at scale. As a result, data scientists want to use the latest and the greatest trends in AI ML software and hardware technologies on their datasets. This is causing an architecturally siloed implementations, where massive data is being ingested into a data lake that needs to be operated by AI ML frameworks, which has to be onboarded to a different platform for processing. It is okay if the demand is seen only on a small percentage of workloads. However, that is not the case. For instance, customers are experiencing continuous data growth, especially in use cases such as IoT, autonomous driving, smart cities, genomics, and financials, to name a few. As a result, the demand for GPU accelerated AI ML processing of this data has increased way more than ever before, and hence becoming the major driving force for key requirements. Furthermore, we are also seeing a convergence of many open source technologies to cater the next generation of data analytics. Cisco Data Intelligence Platform is a cloud scale architecture which brings together big data, AI compute farm, and storage tiers to work together as a single entity, while also being able to scale independently to address the IT issues in the modern data center. This architecture allows for extremely fast data ingest, data engineering done at the data lake. AI compute farm allowing for different types of AI frameworks and compute types, such as GPU, CPU, and FPGA, to work on this data for further analytics. By storage tiers, allowing to gradually retire data which has been worked on to a storage dense system with a lower dollar per terabyte, providing a better total cost of ownership. And seamlessly scale the architecture to thousands of nodes with a single pane of glass management. Cisco Data Intelligence Platform is largely enabled by Hadoop 3.0, Kubernetes, and object store ecosystem working together. Hadoop 3.0 introduced support for Docker container, GPU isolation, and scheduling. Furthermore, it also added deep learning with TensorFlow or PyTorch directly on a Hadoop cluster. Later on, we have seen another staggering and impressive project named Apache Submarine join the AI framework and took this one step further to introduce a fully orchestrated distributed deep learning framework. With this, user can now spawn a distributed job and pool GPU resources from across the cluster. Now with Spark 3.0, we are excited for our data scientists who now have one more option to do this natively within Apache Spark 3.0. This natural evolution of Apache Spark to cater newer form of compute, in this case GPU, provides our customers with more options to analyze their data. From here, I'll be handing over to Ryan Lee, who will be talking about Apache 3.0.
Thanks, Afsal. The existing Apache Spark stack is already a popular framework for big data processing across a wide range of industries. It's well supported by cloud service providers and integrates cleanly with many industry standard machine learning tools like XGBoost and TensorFlow. With these use cases in mind, NVIDIA wants to bring GPU acceleration to existing Spark applications with as few changes to those applications as possible. With the coming Spark 3 release, NVIDIA has engaged with the open source community to enable GPU-aware scheduling of Spark jobs with GPU isolation and explicit allocation of GPU resources. With these changes, Spark can now utilize the existing GPU optimizations of tools like TensorFlow and XGBoost to accelerate existing pipelines already in production. For ETL-focused applications, the newly released Rapids Accelerator for Apache Spark 3 GPU accelerates SQL and data frame operations, with no changes to existing Spark applications. The plugin replaces operators with GPU-optimized equivalents and falls back to Spark CPU operators when no GPU equivalent exists. The Rapids Accelerator for Apache Spark 3 integrates seamlessly to optimize existing applications while removing the need for GPU-specific changes. These tools, combined with Spark 3, pave the way for Spark users to pull GPU resources across thousands of nodes and run GPU-accelerated workloads at scale. I'm going to pass this back to Afzal now for a quick demonstration of a TensorFlow application running on Spark using GPU scheduling and acceleration.
Thank you, Ryan. In this demo, I'll be illustrating how data scientists could take advantage of Apache Spark 3.0 to launch a massive deep learning workload running a TensorFlow application. We both Cisco and NVIDIA teamed up together and set up Spark 3.0 in Cisco Data Intelligence Platform. It further showcases how Yarn pools and schedules GPU resources across nodes for Spark 3.0 executors running distributed job, and how a data scientist can monitor the progress of this job. And at the same time, it showcases how IT admin can monitor the resource utilization. Before we start our demo, let's click on Cluster Overview to see the overall status of the cluster. Specifically, we wanted to see how many GPUs are available. There are 4 GPUs available at the cluster level. Let's click on the Nodes tab. In this setup, we added 2 additional node, identical node in Cisco Data Intelligence Platform cluster. One of the node is Spark 01 and another one is Spark 02. Let's drill down and see the resources inside Spark 01. Like I mentioned before, both the nodes are identical. This node has 2 GPU available. Let's click on the GPU information. There are 2 GPUs. One is Tesla P100 and another one is Tesla T4. Let's go back to the application tab. Let's go to the script. This is a script where we will be submitting Spark job using Spark Submit. Let's review some of the content before we submit the script. Particularly, we are going to submit this job with total number of executors equals to 2. There will be 2 GPUs available for executors, and there will be 2 GPUs allocated per task. And we will be submitting this job in Yarn cluster mode. Let's submit this script. As it is running, let's go back to the Yarn GUI. Refresh the application tab. As you can see, a new job or an application has been submitted and it is currently in running state. Before we go and see inside the application, let's click the cluster overview. As we can see, all the 4 GPUs are currently being utilized. Let's go back to the application tab, click on the application, click on the attempt. As you can see that there is application master and there are 2 executors containers running. And we click on one of the executors. This is provision in Spark 01. Click on that node. As we can see that both the GPUs are currently being utilized. Let's go back. Click the log. As you can see, the training is being performed inside this container. Let's go back to the application. Click on application masters to launch the Spark dashboard. As we can see, Spark dashboard, the event timeline. And let's go to the executor tab. Here we can see the driver is running in Spark 01 node, and one of the executor in Spark 01 and another one in Spark 02. We can also launch the logs from here. Click here for full log, and we scroll down. As you can see, that training is being performed. Let's click on our application if it is completed. Yes, it just got completed with success. Let's go back to the Yarn GUI, refresh it. Yes, the application is completed with success. Let's go back to the cluster overview. As you can see that after the job is completed successfully, all the resources are returned back to the cluster. that concludes this demo. Thanks for watching.